Hi everyone, I'm Minesh, and today I'm going to talk about beer. So I'll start out with a high-level summary of our work. The problem that we tackle in this work is that DRAM on ECC complicates reliability studies by obfuscating DRAM error characteristics. And to overcome this problem, our goal in this work is to understand exactly how on ECC obfuscates errors. Now, to achieve this goal, we make two contributions. First, we introduce beer, which is a new testing methodology that determines a DRAM chip's unique on ECC function. In other words, its parity check matrix. And second, we introduced beep, which is a new testing methodology that infers raw bit error locations of error-prone cells using only the observed uncorrectable errors. Finally, we evaluate beer in two different ways. First, we experimentally demonstrate beer using 80 real LPDDR4 DRAM chips from 3 major DRAM manufacturers. And second, to complement our experimental studies, we show beer's correctness and practicality for over 100,000 representative ECC codes using simulation. Now I'll give an overview of our work in a little more detail. So third-party DRAM users, such as system architects who design error mitigations at the system level, test engineers who perform extensive third-party testing and validation studies, and research scientists who conduct experimental error characterization studies, all need to understand a DRAM chip's reliability characteristics in order to effectively do their work. And these sorts of characteristics include things like looking at manufacturing variation between different DRAM chips and locations of weak cells within a DRAM chip, and so forth, as shown on this slide. So the way that these people determine these properties is using extensive DRAM testing and error characterization. So given a DRAM chip, they study the observed bit flips when errors occur. However, modern DRAM chips incorporate on-die error correction codes, or ECC, which are unknown and proprietary, provide no feedback to the CPU on error correction, and therefore on-die ECC obfuscates the errors that we're trying to study. And this essentially means that on-die ECC complicates reliability studies by unpredictably obfuscating raw bit errors. Now, to overcome these challenges, our goal in this work is to determine exactly how on-die ECC obfuscates errors, and we can do this by determining its parity check matrix. Now, in the context of a real DRAM chip, this means that we want to know exactly what happens within the ECC logic, because by doing this, we can reveal exactly how on-die ECC scrambles errors, and this allows us to infer raw bit error locations. And to achieve these, we introduced two new testing methodologies, beer and beep, and now I'll talk about these methodologies. So both beer and beep are based on the key idea that disabling DRAM refresh induces data retention errors only within charged cells. And so here we illustrate the two states that a single DRAM cell can be found in. On the left, the cell's storage capacitor is shown as fully charged, and we refer to this as the charged state. On the right, the cell storage capacitor is discharged, and we refer to this as the discharged state. Now, when we induce data retention errors, we can typically cause a charged state to fail to the discharged state. However, an already discharged cell typically will not flip to the charged state. And this means that we can selectively induce errors by controlling bit flip directions. So using this principle, we developed beer, which is a new three-step testing methodology that first induces uncorrectable data retention errors by disabling DRAM refresh operations, then identifies which uncorrectable errors are and are not possible, and finally solves for the parity check matrix using a SAT solver. So let's take a look at each of these steps individually. In the first step, we start with a set of carefully chosen test patterns, where only some of the bits are set to the charged state. Next, we disable DRAM refresh to induce uncorrectable data retention errors. And finally, we observe different error patterns for each test pattern across all of the different ECC words within a given DRAM chip. Now note that these errors only occur within specific bit positions because not all bits are set to the charged state. In our second step, we identify which uncorrectable errors are and are not possible for each test pattern. And in order to do this, we make a table of the different test patterns and itemize which of these bits are actually susceptible to errors and which are not. And this is very important because this table will be different for different ECC functions. Finally, we solve for the parity check matrix. And to do so, we input the table of possible errors and the basic properties of a Hamming code as constraints to a SAT solver. And upon evaluating the SAT problem, we get the parity check matrix that's responsible for the observed error patterns. In summary, beer determines the parity check matrix without hardware support or tools, prior knowledge about the on-die ECC mechanism, or access to any of the ECC metadata, for example, the error syndromes that it generates. And finally, we open source beer as a project on GitHub at the link shown on the slide. Now, we evaluate beer in two different ways. First, we provide an experimental demonstration using 80 real LPDDR4 DRAM chips from 3 major DRAM manufacturers. And second, in simulation to show beer's correctness and practicality for various representative on-die ECC codes. Now, our experimental studies show that different manufacturers appear to use different parity check matrices, whereas chips of the same model number actually appear to use identical parity check matrices. And our simulation results show that beer works for all simulated test cases, and beer is practical in terms of both runtime and memory usage. Finally, we show how knowing the parity check matrix via Beer is useful in practice within our paper. We show this for designing systems that are designing reliable systems, for efficient testing and validation, and for performing effective error characterization studies. And if you're interested in these use cases in more detail, please take a look at our paper where we explain each of these three. And finally, thank you for attending my session, and I'm happy to take any questions at this time.
Thank you. The first question is, what is your recommendation on the ECC usage provided by vendor? It sounds like you would like disable it, but use an ECC algorithm known to the end user to avoid scenarios you describe in the talk. Is that correct?
Right. Yeah. That's a great question. So I think we have two different perspectives on this. So the first perspective is that realistically, manufacturers are unlikely to just entirely disable OnDie-ECC or to fully expose it, because it's very closely tied to their manufacturing yield. And they need this to sort of keep the yield numbers that they want. And in this case, we hope that manufacturers will use our work as sort of a sign that maybe they can be open about certain aspects of the OnDie-ECC mechanism. And by communicating these aspects to the system designers or the testers or the research engineers, some of the information is available, and potentially enough such that these people can do a better job of using these black box OnDie-ECC mechanisms. The second thought that we have is that ideally the OnDie-ECC mechanism would be fully standardized. And so even within the specification, the full parity check matrix would just be specified. And this could be developed by the JDEC consortium or by the manufacturer providing this within the data sheet. But either way, we hope that some information will be communicated, if not all of it. Does that answer the question?
Yeah, I think so. I actually have a related question. So if the industry doesn't act the way we wish them to, right? So if, say, the DRAM vendor really wants to make it more challenging for a work like yours, then a simple way to do it is to not send the decoded value, because that's how you did the reverse engineer, right? So is that the case? Do they have to send the decoded value of the uncorrectable error back? Or is it simply if they don't send it, it's still the system will work functionally, but your technique will not work?
So I believe, so the system is sending the corrected value back. So excuse me, the DRAM chip is sending the corrected value back, and the intermediate results are not sent back to the system with OnDie-ECC. So in our work, we're actually inferring all of this information about the ECC mechanism without looking at the intermediate steps. So for example, the encoded data or the decoded data before correction, those two are actually invisible to us. And the reason that our work, we can do this is because we're able to inject errors essentially in the post-correction data. Excuse me, in the data that is actually stored within the DRAM device before it's corrected, by exploiting these data retention errors. And so the current OnDie-ECC system already exposes the minimum possible data, right? Because it's giving us only the corrected data back. So
if it's corrected data, then all of the vendor will send the same corrected data back. I thought your work is about exploiting the detectable and correctable error variation to figure out which ECC they use.
Right. So in the current OnDie-ECC implementations, when there's corrupted data, the different vendors will actually send back different data, because the uncorrected errors actually depend on the parity check matrix that's used. And so right now, the different manufacturers, we might read different uncorrected data patterns for the same types of errors that actually occurred within the DRAM chip. And so that's what sort of the difference is here.
Right.
If the manufacturers were to somehow mask that and send some... So I'm not clear on exactly what your question is. Sorry.
Right, my question is, in the case of detectable and correctable error, yes, the data received on the processor side would be the corrected data, but it is wrong, right? Since it is a detectable and correctable error, then why would the DRAM be obligated to send back the corrupted data? A simple way to make your technique not working is to not send that data.
So what data do you suppose that they would send instead? Like they would simply not send any data whatsoever?
Or a signal that says this is a detectable and correctable error.
I see. Yeah, so right now there's no such signal, and there's yeah, so we don't have any information that comes back at all about an error correction event or an error detection. And it's just blindly returning the data, whether the data is corrected or not. So yeah, I agree. If the standard was changed such that there was some signal that signaled a correction event, but it was uncorrectable, then yeah, we would not see the uncorrected error patterns. That's right.
I see. Thank you. Any other questions from the audience? I have one more question. Looks like the proposed technique has many potential use cases. One possible use case could also be some security related, like row hammer. Do you have any comment on potential security related use cases, and how would that help either the attacker or system designer?
Right. No, that's actually a great question. So in the Security and Privacy Conference in 2019, there was a paper published that applied a reverse engineering technique to the ECC code of the rank level ECC. So this is the ECC that's done within the memory controller of the CPU. And by reverse engineering that code, the attackers were able to develop test patterns that would, so they'd know exactly what the post encoding data would be when they write specific data to the DRAM chip. And so essentially you can control where these row hammer bit flips would occur. And so we believe a similar technique could potentially be applied here, because after applying our methodology, you would know exactly how the data you're writing is going to be encoded by the ECC mechanism. And so you have an idea of what exactly is going to be written to the physical cells. Now, if there's some property of the physical devices that the physical cells themselves that enables you to, say, increase the row hammer error rates or some other error mechanism, you could certainly exploit this in the sense of test patterns. As far as detecting errors, I'm not certain exactly how that would work, because here, essentially, because the on.ECC mechanism does not report any correction or detection information back to the system, if there is a single bit flip that occurs and the on.ECC mechanism corrects that, there's no information that such a bit flip occurred at all. Whereas in the rank level ECC, potentially there is a signal sent by the memory controller saying that, oh, we corrected a detectable error. And so in that sense, on.ECC will still mask a single bit error. But in the event of multi-bit errors, it may enable, knowing the parity check matrix may enable us to figure out exactly which bits are responsible in the underlying hardware itself and construct test patterns that take advantage of that.
Okay, thank you. There's another question from Anand. How can DRAM cannot send? Can you elaborate on that question, Anand? I'm actually not sure what that question means.
Right.
Okay. Maybe we can reach him after the talk. Thank you again, Minesh, for giving a wonderful talk. Let's all thank the speaker and maybe move to the next one. Thank you very much.
Thank you, Dr. Pro.